Okay, so in lesson 24 we're going to talk about alpha-beta unsaturated aldehydes and ketones. So an unsaturated bond, as you recall, is a double bond of some sort. And in this case, if this is your carboxyl group, this would be the alpha position, and the next one would be the beta position. So what that essentially means is a double bond that's sort of conjugated, if you will, with that C-double-O bond there. Now, you can go through two different types of resonance structures here. Electrons can go up, and you'll end up with a positive charge on that carbon, right? Sorry, I had to work the R in here. I kind of forgot to write it in earlier. So in this case, if this were sort of the place where you cut the aldehyde in, then the nucleophile will sort of attach right there. However, if this is allowed to establish equilibrium again, these electrons could be over here, at which point you can end up with a positive charge at the beta position. So in this case, if the nucleophile were to attack, it would go right here. We refer to this as conjugate addition, and we refer to this product would be direct addition if a nucleophile were to attach to either of them. So we have to figure out what's going to happen and who's going to go where. It's kind of simple in a little bit of a way. If you have a weak base, so there's a whole list here: fluorine, halides, Cm-, HS-, alcohols, amines, and even your favorite organocuprate, then what ends up happening is as you get the direct addition, this is in equilibrium. Well, so if it goes up here, it comes back down. It goes up here, it comes back down. It goes up here, it comes back down, and it goes here. As soon as it goes to this position, it's no longer in equilibrium. It's a thermodynamic product. This is the sink. Therefore, this is your major product that you end up getting. And as this continues to go in equilibrium, you're removing this by moving it here, right? So the equilibrium will shift here until you essentially end up getting almost all of your product in this state. Now, strong bases are a bit different. So strong bases such as Grignards and hydrides, in this case, you can actually get both of them and there is no equilibrium. However, most of the time, this is really only going to give you a majority of one product because of the fact that this is the most reactive site, is the C-double-O bond right here, okay? Because it's got the strongest polarity to that particular bond. So as long as this C-double-O bond is accessible, in other words, you don't have a huge, like a terp-butyl group or something like that in this area, then this is going to be the vast majority of your product, especially if it's an aldehyde. If it's more sterically hindered, like a terp-butyl or something like that, you might end up getting both of those. So we try to avoid that in most of our synthesis and how we design things. Okay. Well, you also have to consider carboxylic acid derivatives, and by that what we mean is anything like this, so our acyl chlorides or esters, anything that basically has a COO bond in it. If you can actually provide an elimination substitution reaction, that's what's going to happen first. If you've got a less reactive type of situation like this, we've got an ester, then the conjugate addition product might form. So here's what we mean by that. This Cl can still be replaced by that, right? Well, that's pretty easily done because this is more stable on its own than this is. So bam, you end up getting the amide. On the other hand, this is an ester. Cl- is kind of happier on its own than would be an OR-. Therefore, this guy is going to add to the beta position. And that's the difference in them. Okay, thank you very much.